Look up at the night sky. Stare into the endless black, dotted with stars, galaxies and nebulas that stretch farther than our eyes can see, farther than our most powerful telescopes can reach. For thousands of years, humans have gazed upward and asked two of the biggest questions in existence. Where did we come from? And where are we going? We've unlocked the story of the Big Bang, the fiery, explosive birth of our universe 13.8 billion years ago. We've mapped the galaxies, measured the expansion of space, and peered into the darkest corners of the cosmos. Scientists have spent decades studying the fabric of space-time, the force of gravity, and the mysterious energy that pushes the cosmos apart. What they've discovered is not one, but three possible ultimate fates for everything we know. Three paths that lead to the end of all stars, all planets, all life, and even the very structure of space itself. These are the Big Crunch, the Big Freeze, and the Big Rip. Three endings that will redefine everything we think we know about time, space, and existence. Let us begin this journey into the far, far future of the universe. A future so distant, it makes the age of Earth seem like a single blink of an eye. First, let us explore the Big Crunch. This is the cosmic fate that was once the most widely accepted idea before we made the shocking discovery of dark energy. The Big Crunch is simple. In its core logic, what goes up must come down. The universe began with the Big Bang, a rapid expansion that flung all matter and energy outward in every direction. For billions of years, gravity, the invisible force that pulls planets toward stars, stars toward galaxies, and galaxies toward one another, has been fighting against that expansion. If gravity were strong enough to overcome the universe's expansion, the outward push would slow, stop, and then reverse. Imagine blowing up a balloon as big as you can, then letting the air rush back in. As the Big Crunch galaxies that are now speeding away from each other would start to drift closer. Clusters of galaxies would collide and merge. The space between stars would shrink. Over trillions upon trillions of years, the entire universe would contract, growing smaller, hotter, and denser with every passing moment. Stars would smash into one another. Galaxies would crumple into supermassive black holes, and all matter in the cosmos would be pulled back into a single, infinitely dense point, a singularity. This singularity would be exactly like the one that birthed the universe in the Big Bang. Some scientists even wonder if the Big Crunch would lead to a new Big Bang, creating a cycle of birth, death, and rebirth for the universe. A cosmic loop with no beginning and no end. But for us, and for every form of life that ever exists, the Big Crunch means a fiery, compressed end to all things. No stars, no planets, no light, just a single silent point of infinite density. But here's the twist. In the 1990s, astronomers made a discovery that changed everything. They were studying distant supernovae to measure how fast the universe was expanding, expecting to find that gravity was slowing the expansion down. Instead, they found the exact opposite. The universe is not slowing down, it is speeding up. The expansion is accelerating. And the force driving this acceleration is something we cannot see, cannot touch, and barely understand: dark energy. Dark energy makes up about 68% of the entire universe. It has the invisible hand pushing space apart, stretching the fabric of the cosmos faster and faster with every passing second. This discovery ruled out the Big Crunch as the most likely fate, at least for now. Which brings us to the second, and currently most probable end of the universe, the Big Freeze. The Big Freeze, also known as the heat death of the universe, is the quiet, cold, and lonely end to everything. This fate relies on one simple rule of physics, the second law of thermodynamics. This law tells us that everything in the universe moves from order to disorder, from hot to cold, from energy to entropy. Entropy is the measure of chaos in the universe, and it always increases. With dark energy pushing the universe to expand forever, galaxies will continue to drift apart. The space between them will grow so vast that light from one galaxy will never reach another. Each galaxy will become an island alone in the endless black of space. Over time, stars will burn through their fuel. Small stars like our sun will swell into red giants, then fade into white dwarfs. Massive stars will explode in supernovae, leaving behind neutron stars or black holes. Eventually, no new stars will form. The cosmos will go dark. The last stars will flicker out, leaving only cold, dead stellar remnants. Black holes will slowly evaporate through a process called Hawking radiation, trillions of years in the making. Once the last black hole is gone, the universe will be filled with nothing but low-energy photons, neutrinos, and other subatomic particles, spread thin across an infinitely large, cold, dark space. The temperature of the entire universe will drop to just a fraction of a degree above absolute zero, the coldest possible temperature. There will be no energy left to power any motion, any life, any change. Time itself will lose meaning because nothing will ever happen again. The universe will be a vast, silent, frozen void. This is the Big Freeze, a slow, peaceful, but utterly lonely end to all existence. It is the fate that most cosmologists believe is the most likely given what we know about dark energy today. But there's a third, even more terrifying and violent possibility, the Big Rip. This is the most extreme end of the universe, a fate so destructive, it tears apart the very fabric of space-time itself. The Big Rip theory hinges on a terrifying idea. What if dark energy doesn't stay constant? What if it grows stronger and stronger over time, becoming a force so powerful it overwhelms every other force in the universe? Gravity, electromagnetism, even the strong nuclear force that holds atoms together. Right now, dark energy is pushing galaxies apart, but it is not strong enough to tear apart individual galaxies, stars, or planets. Gravity still holds our Milky Way together, and Earth stays orbiting the Sunday. But if dark energy's strength increases exponentially, everything changes. First, dark energy will overpower the gravity that holds galaxy clusters together. Clusters will split apart. Then, it will tear apart individual galaxies. Stars will be flung away from their galactic centers, drifting alone in space. Next, solar systems will break apart. Planets will be ripped from their stars, moons from their planets. Then, the forces that hold stars and planets together will fail. Stars will explode, planets will shatter into dust. Finally, dark energy will become so strong that it tears apart molecules, atoms, and even the subatomic particles that make up all matter. Protons, neutrons, electrons, everything will be ripped apart into fundamental particles. And in the end, dark energy will tear the very fabric of space-time itself, leaving nothing but a chaotic, broken void where the universe once was. The Big Rip is the most violent end imaginable. It is not a slow fade or a compressed collapse. It's a sudden, unstoppable, tearing apart of every single thing in existence. And while it is less likely than the Big Freeze right now, we still know so little about dark energy that we can't rule it out entirely. So, which of these three fates awaits our universe? The answer lies in understanding dark energy, the most mysterious substance in the cosmos. We know it exists. We know it, accelerating the universe as expansion. But we have no idea what it is. Is it a constant force, as Einstein once proposed with his cosmological constant? Is it a dynamic field that changes over time, called quintessence? Could it fade away, letting gravity take over and lead to the Big Crunch? Could it grow stronger, leading to the Big Rip? Or will it stay constant, leading to the Big Freeze? NASA's space telescopes, like the Hubble Space Telescope, the James Webb Space Telescope, and the upcoming Nancy Grace Roman Space Telescope, are working around the clock to answer these questions. They re-measuring the expansion of the universe with unprecedented precision, mapping dark energy, and studying the distant galaxies that hold the clues to our cosmic future. Every time we look deeper into space, we learn something new that changes our understanding of the universe. 100 years ago, we didn't know the universe was expanding. 50 years ago, we didn't know dark energy existed. 10 years ago, we hadn't seen the first galaxies formed after the Big Bang. The more we explore, the more we realize how much we have left to discover. Think about how small we are. Our planet is a tiny blue dot orbiting an ordinary star in a galaxy with 100 billion stars in a universe with 2 trillion galaxies. Our entire existence is a fleeting moment in the cosmic timeline. But even though we re small, we have the ability to ask these big questions. We have the curiosity to look up the intelligence, to calculate, and the courage to explore the farthest reaches of space and time. The three fates of the universe, the Big Crunch, the Big Freeze, the Big Rip, are not just stories about the end of everything. They re a testament to the power of science, the wonder of the cosmos, and the human spirit that refuses to stop looking for answers. We may never live to see the end of the universe, but we can spend our lives understanding it, marveling at it, and exploring every secret it holds. The universe is vast, mysterious, and beautiful. It began with a bang, and it will end with one of these three extraordinary fates. And as long as we keep looking up, keep asking questions, and keep exploring, we will always be a part of its incredible story. Please like, comment, share, and subscribe to the channel.